All right, so looking back at the valence electrons, so we could predict whether these elements are going to gain or lose electrons to become like their noble gases and have that same configuration. Remember, it's all about stability in the lowest energy aggregate possible. And following the group numbers, like group 1 has 1 valence electron, group 2. So these ones follow the 1 or the 1A, 2 or 2A, no problem. But when you get over here, this is really 13, but you could call it 3A and know that it has 3 valence electrons, 4A, 4 valence electrons, 5 valence electrons, 6, 7, and then 8, remember that starts with neon. Helium is special. Helium has 2 valence electrons. So don't forget that notable exception. But the idea, of course, is to attain a noble gas configuration in order to achieve stability. Now, we're talking about in terms of ions now. This is a way to do it. There's also another way. It's called covalent bonding, which we'll discuss later in a future unit. So lithium, remember lithium's right here. That's lithium. No, that's hydrogen. Sorry, lithium's down here. The second block here. Lithium has 1 valence electron, and we talked about it last time. So lithium's going to lose that 1 valence electron. So it becomes Li+. And all of the elements in that particular group, the alkali metals, we're talking sodium, potassium, rubidium, cesium, all the ones that go down that group, they all have 1 valence electron, and they're all going to come to that formal charge of plus in this particular case, because it's easier to lose 1 than to gain 7. So lithium's choices are to mimic helium or mimic neon. So losing 1 makes it mimic helium's configuration. Gaining 7 would make it have neon's configuration. So it's easier for lithium to lose 1 and look like helium. And the element below lithium in that group would be sodium. And so it's the same thing. Sodium can lose 1 electron. Now it looks like neon. And then potassium, which is below sodium, it will lose 1 electron, and now it looks like argon. Okay, so you're kind of getting the idea here. Beryllium is the first one here in group 2. That one's going to lose as well, and it loses 2 electrons, though, because it has 2 valence electrons, so the formal charge on it would be 2+. Aluminum's down here in this purple section right here. It's in the boron group. Remember, boron's a metalloid. It kind of does different things in the way that it bonds, but typically if we're going to group it with 1, it's going to mimic the helium noble gas rather than the neon one. But aluminum right here has the 3 valence electrons, so it's easier for aluminum to give away 3 or lose 3 than to gain 5. So aluminum's a loser too, and you're seeing a normal trend here is that the ones that are metals are typically going to be losers. They're going to be the cations. So it's Al3+ if I'm writing out the formal charge here. Carbon's right here. Carbon, and these guys right here, the ones that are in the carbon group, this is silicon, and below silicon happens to be germanium. So silicon and germanium are metalloids, and carbon is a nonmetal, and then down here we get tin and lead in here. So this group is kind of a variance group. You start with nonmetals and it gradually becomes more metallic as you go down the group. I would say for these guys right here, carbon, silicon, germanium, these non-metal metalloids, they're typically going to share. They're not going to really form ions, but with 4 valence electrons, if it had to form an ion, it could lose 4 or gain 4. So this is where we put lose or gain. Can be either. Now with carbon, if it loses, it's going to be 4+. Carbon, if it gains, would be 4-. So that's why we put the plus or minus 4 in there. Nitrogen group. That's going to be like phosphorus, also arsenic in here, antimony, and then it becomes more metallic. But these guys, if they're going to form ions, they have 5 valence electrons now. So 5, it's easier for them to gain 3 rather than to lose 5. And nitrogen is a nonmetal, so as you can see, Non-metals typically form the anions based off of their property listing. When we're listing their properties, they're anions typically. If they're going to form ions, so nitrogen would be 3 minus because it's going to gain 3 electrons. If it gains 3 electrons, then now it looks like neon. Oxygen right here is going to do the same thing. It has 6 valence electrons. It's going to gain O minus 2 and look like neon, 2 electrons. And then last but not least are halogens, which are the most reactive nonmetals because they only have to gain 1 electron in order to become stable. So F would just get a minus charge, gain 1 electron. Now it looks like neon and it's very happy. Neon is a noble gas already, so it's going to be the neither category because neon already has those 8 valence electrons and is not seeking any type of need for stability because it's already stable on its own. So it doesn't need to bond with anything. And actually, helium, neon, argon, none of those ever bond with anything. There's a few exceptions for krypton, but you have to give it lots of energy. Kind of have to like force it. And xenon, super big xenon, can do a few compounds, but that's based off of, also applying energy to make it. So you're really creating a less stable configuration for it by making it and forcing it to bond with other elements. But a few exceptions in the noble gas range of being capable of forming compounds. Now this one's just going back over, looking here. Elements that lose electrons are going to be the metals. So you want to highlight that one. They're the ones that form the cations. Cations are the positively charged because they lose electrons, and the ones that gain electrons, of course, we classify typically under here as the metals. Now, some of the metalloids, like I said, do funny things, but this is our general rule we're going to follow. They're going to be the anions. They're going to gain those electrons. Now, before we continue on, just want to go back over that valence electron system, 1A, 2A, 3A, and so forth, because now we're going to use the valence electrons to represent the Lewis dot structures. They're a little bit different, and applying those valence electrons. Helium, of course, still only has 2, so I noted that exception again, just to make sure we're all getting that. What is a Lewis dot structure? We're going to use those A groups here, that A grouping, to figure out our valence electrons. And basically what you're going to do is you're going to use the number of valence electrons, and they're going to correspond to dots that we write around the symbol. And this is a visual way that we're going to use, and also later on, to form bonds. So we're going to actually use the dot structures, the Lewis dot structures, to create compounds. But this is the basic one. First, we have to write them with their elements and just their symbols. And then we'll get into the more complex, where we're actually combining different elements together to form compounds. What the major rule here is, you count up the dots and then you just put 1 on each side before you pair them up. And it really doesn't matter which side. So I put this chart in here. This is one way you could do it. It doesn't have to be the only way. Like for instance, for these guys, group 1A, they all have 1 dot because they have 1 valence electron. But for sodium, it doesn't matter if I put the dot here or put the dot on this side. You can pretty much put the dot on any side. It really doesn't matter. Just so you know. And then if I'm looking here at group 2, the alkaline earth metals, they have 2 valence electrons. So if I wanted to do magnesium, I always do it clockwise. I start right and then down. This is still acceptable. You could put them like that. They just have to be on different sides. You could do this way. Okay, it really doesn't matter, just as long as they're on separate sides. Group 13, the boron group, 3 dots. Once again, like if I wanted to write aluminum, I don't have to put them on that. I could do that. This is my normal pattern. I start and I go clockwise. But just as long as you have 1 dot on each side, don't pair them up. This would be incorrect if I did this. And I put 2 right here. Like that would not be correct. I need to put 1 dot on each side. At this point, the one dot on each side is representing the possibility of a bond happening. So carbon group, we already looked at carbon, but one on each side. They're always going to have one on each side. Now when you get to the nitrogen group, you look here. Nope, that would be incorrect. Got to fix that. So you could write it like this. Uh-oh, sorry, hold on. Got to get rid of the eraser. There we go. Okay. Nitrogen, you could do 1, 2, 3, 4, and then make this the pair on the bottom. It really doesn't matter. But what you'll notice, that means it has 3 different places that it can bond. And that's what we're going to use these for later on. Oxygen 2, 1, 2, 3, 4, 5, 6. You could do it that way. That's how I do it. I always do it clockwise, or that one doesn't look very good, so I'm going to fix that. Oops, I erased the O. Doing really good with my pen today. Come on. There we go. Let's put the O back in here. And then put the other ones right here, kind of like in a little pair. Really doesn't matter which side, but you would have to pair 2 of them up, basically. So this one can do 2 bonds. And then fluorine, chlorine, bromine, iodine, they have 7. So it really doesn't matter which side you leave open, but as you'll be able to see, they can form one bond like so. Now the reason why we put helium like this, where we put the 2 together, is because helium's already stable on its own. So it's not going to form any bonds, so like we keep the dots closed, they're already a pair. So we wouldn't leave one open as a bond possibility. And then as you can see for the rest of the noble gases, they have 2 on each side because they have a total of 8 valence electrons. Now let's do some practice. So your turn here, like looking at X. This is some generic element that has 5 dots around it. What do those 5 dots mean? What group? How many valence electrons? What do we got going on here for X? Five valence electrons. Good. So we know there's 5 valence electrons, 5 dots. So what group? That group 15. I see that. Very good. So this is group 15. Very good. So I'm going to cross that one off because put that one in the right spot. Now I need to look at my periodic table and look for other elements that would be group 15. So what other ones in here could go here and have the 5 dot arrangement like so? Yes, so phosphorus is a group 15 element, so I'll cross that one out. And yes, arsenic, or As, also belongs here. So you would want to sort those ones over to that particular part for doing that slide. So go ahead and take a moment to do Z and Q, and we'll come back in just a minute. Okay, so what do we get for Z here? How many valence electrons? 7. Good. So 7 valence electrons. That means I must be in group which one? Group 17. Boom. Halogens. Yes, group 17 goes here. And what elements are group 17 elements up here that we see that would have that kind of Lewis dot diagram, or the possibility of that? Good. Fluorine and bromine. They fit in that category. So I'm going to cross those off. Cross these ones off. So I'm not going to use those choices. They're already used. Now Q. What group is Q elements going to come from? Group 13, 3 valence electrons. Very good. Group 13. So cross that one off. What are my group 13 elements up here that I would sort over? Yes, aluminum. Good. And gallium. Very good. So aluminum and gallium, those ones go. Now, group 1, there isn't one up here for group 1 because group 1 would just have 1 dot. Group 18, they would have 8 dots. mainly because neon down would have 8 for 8 valence electrons. So krypton would be in group 18. Calcium's actually group 2, which would be 2 dots for alkaline earth metals, and then rubidium is the one that would match that group. But we're not using those choices, so we just leave them over to the right. Few things to note here about our transition metals and a few key ones that we have to kind of just memorize their oxidation numbers and states. Now, basically what we figured out on 2 slides ago was that they gain and lose electrons to be like the noble gas configurations. So we pretty much use this pattern. Everything in group 1, alkali metals and hydrogen, when they form a charge, they're going to do +1. They're going to lose 1 valence electron. So everything here, so lithium, sodium, potassium, rubidium, cesium, francium, all of these guys will going to form this +1 oxidation number or charge. So if I were to ever write their ions out, like K would be plus, CS would be plus, and so forth. This group, group 2, alkaline earth metals, beryllium, magnesium, calcium, I think it's strontium, then barium. I don't even know what the last one is, but that's okay. So all of these guys are going to be +2. So if I write out calcium, it would be +2 if I'm talking about a calcium ion, or a strontium ion, +2. So this pattern goes +1, +2, then group 13 over here is +3 group. So that's going to be aluminum, gallium, indium, these guys right here. Now boron kind of does its own thing. Boron doesn't really typically form ions, but these guys I would all put there, like Ga could be 3+, and so forth. 3 valence electrons, gonna lose, and so forth. Carbon group, the carbon, silicon, germanium, this is going to be what, tin and lead, Pb. Now this is where the break is, because these guys are metalloids and these guys are actually metals. So tin and lead are interesting metals. As you can see here, you're going to sort these cards. They go here. Actually, I'm going to change colors so it makes it easier and more obvious. We'll make that a green color. How about that? So I'm going to go ahead and circle these guys, tin and lead. I'm going to put them in green. Now they can go to +2 or +4, and this is why. That means they can sometimes lose 2 electrons or sometimes lose 4 electrons, depending upon how they're reacting. So we call ones that have more than one charge multiple oxidation metals, or MOMs, multiple oxidation metals. And most of the multiple oxidation metals are going to be here in the transition metals section. Tin and lead, though, are a little bit outside that section. But if you think about it, when tin or lead loses 2 electrons, they lose it out of their P's here. So the 2 P's are going to go. If they lose 4, they lose the P's and the S's over here. Because remember, we always take out the electrons from the higher energy levels. So you're going to lose them from the P's first, then the S's from the configuration. And they have this full D block. Both of their D blocks are completely full. So they're stable either way. They can lose 2 or they can lose 4. And that's one that you just kind of have to memorize. You have to just memorize these guys. Now there's other elements in here like 1, 2, 3, 4, 5, 6. Here's iron. Iron can go to +2 or +3. Next to iron is cobalt, which can do +2 or +3. Next to that, 2 over is copper. Copper can do +1 or +2. Really depends on the different metals, what their multiple oxidation ability is. The reason why they have the ability to form more than one oxidation state or charge and lose different amounts of electrons is because they have the d orbitals. So they'll lose their s electrons, and then they'll lose, if it's an additional one like the 3, they'll lose some out of their d block. and it still remains stable in those particular cases. Manganese is pretty funny too, because manganese right here has like 5 oxidation states, and you saw probably on the slide that has +7. Well, that means it loses the 2 out of the S and the 5 out of the D, and so when manganese Mn does +7, it actually looks over here like argon. It mimics the argon configuration. So that's kind of an interesting one. But manganese can do +2, it can do +3, it can do like +4, I think. It has like 5 different oxidation states. It's definitely one of the stranger groupings in the transition metal section. So now we talked about the multiple oxidation metals. Those are in green. Now we're going to talk about these unique ones right here: silver, zinc, and cadmium. Silver, zinc, and cadmium are over here in the transition section as well, but these guys only have one possible oxidation state, one possible charge. Like silver only loses 1 electron. So silver is always going to be +1. Always, always. So you kind of have to memorize that. You're going to need that later on for naming. Zinc is right here. Zinc always, always goes to +2, which kind of makes sense because it loses the 2 out of the S here, and then its D block is completely full. Cadmium, same deal. Cadmium's right below zinc. This one loses the 2 out of the S, and then the D block is completely full. So we kind of have to memorize these. Now there's an easy way to remember zinc and silver. If you look at the diagonal from aluminum, because aluminum's +3, zinc is +2, silver's +1. So it goes in this nice little diagonal to help you remember. You just remember aluminum's +3 because it's in group 13, has 3 valence electrons. The zinc has +2, 1 less. The silver has 1 less, +1. Cadmium, you just kind of have to memorize. And then our lovely tin and lead, make sure you memorize those two as well. The rest of them that you don't have to memorize anything else in this section, so don't worry about that. But you do have to know, like, group 1 is +1, group 2 is +2, group 13 is +3, 14 is ±4, 15 is -3, 16 is -2, halogens or 17 is -1, and then the noble gases always go to formal charge of 0. So remember that pattern. It goes up to 4. So plus, 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 like +1, +2, +3, +4, -4, and then it goes down the other direction. But it's a nice pattern on the periodic table to being able to know most of these atoms, these elements, what their oxidation numbers are. Last but not least here, we're going to talk about 2 more terms called oxidation and reduction. Oxidation, reduction. And later on, when we get to reactions, these ones that involve oxidation reduction, they're called redox reactions. You might have heard of redox before, but that's where it is. Like the ox part is oxidation, the red part is reduction. When you lose electrons, you become cations, that's called oxidation. When you gain electrons, you become anions, that's called reduction. So based off of this, looking at our little slides here of what we need to sort, ones that are cations that lost electrons, those obviously go in the oxidation category. So over here in oxidized, I would put the manganese 7. Done that one. The hydrogen, it has a plus. It lost an electron, so it's been oxidized. The oxygen one here, which is technically called oxide, but it has gained 2 electrons. That one has been reduced, so I would put it here in the reduction category because it gained electrons. Zinc has a +2, that means it lost electrons, so it goes over here in the oxidized category. Chloride, Cl-, gained an electron, belongs in the reduced. Iron 2, +2, oxidized, gained or lost 2 electrons. Calcium, lost 2 electrons. And sodium, lost 1 electron, excuse me, because it only has a plus. And then phosphide here, this is the phosphorus ion, P -3. And so just 2 more terms there between cation, anion, oxidation, and reduction.